Chemical formulas is next on the list. Chemical formulas represents a makeup of compounds and molecules. So for either one, we will need chemical formulas for determining compounds and molecules. A molecular formula uses symbols to show us what atoms are present, and it also uses subscripts to show us how many of each type are in a molecule. For instance, H2O for water means 2 hydrogen atoms and 1 oxygen atom. And subscripts, they're only used when more than one atom is present. So if we just had, if we didn't have any more than one, we would just put the symbol itself. And the structural formula, it tells us all of the same information as a molecular formula, but it also shows us how the atoms are connected. So it gives us more detail showing how the atoms are bonded, and this can be used, represented using models like what's called a ball and stick model and space-filling structures. So if we take a look at this figure here, all 4 of these representations represents a methane molecule. So for letter A, we have the molecular formula CH4. B is the structural formula, and it shows the bonds there between hydrogen and carbon. C is what's called a ball and stick model, and D is a space-filling model. These different views help chemists visualize both the composition and the 3D shape of these molecules. There are some elements that exist as molecules, so not all elements exist as single atoms. Some of these elements, they occur naturally as molecules themselves. For instance, there are diatomic molecules, such as diatomic hydrogen, nitrogen, oxygen, fluorine, chlorine, actually that would be chloride. And one of the most common forms of elemental sulfur exists in a ring of 8 sulfur atoms. We write it sulfur S8. And these forms tend to be more stable than their isolated atoms for these elements. And that's why they are creating these molecules, these diatomic molecules. This is what a sulfur molecule would look like with 8 sulfur atoms. A shows us the structural formula showing a ring of sulfur atoms. B is the ball and stick model, and C is the space-filling model. Each of these yellow spheres, they represent a sulfur atom. And sulfur exists in this form as well because it's in its most stable state this way. Each symbol means something different here. So H just means we have 1 hydrogen atom. Here, 2H means 2 hydrogen atoms, but H2 means a hydrogen molecule or diatomic hydrogen. And here we have 2H2. So we have, here's the H2, and we have 2 of them. And so that's how we can represent these molecules differently. Empirical formulas are a bit interesting. They have to do with the ratios of atoms in a compound. So a molecular formula shows the actual number of atoms. For instance, for benzene, the molecular formula is C6H6. But the empirical formula is just CH. And the reason being is we can divide both the carbon and the hydrogen by 6. And because we can divide both of those by 6, we can simplify it to just CH. If we have acetic acid, C2H4O2, the empirical formula for that is CH2O. And here we're dividing by 2. So we divide carbon, C2 divided by 2, we get C. H4 divided by 2, we get H2. And O2 divided by 2, we get O. So the empirical formula reduces the molecular formula to its lowest whole number ratio. Now, this slide shows benzene in multiple different forms. So again, we have the structural formula in A, B is the ball and stick model, C is the space filling model, and D is actually what benzene looks like. It's a photo of benzene. It's a clear liquid, and it's produced during oil refining, and it's used in a lot of different industrial products. Acetic acid is in vinegar. Its molecular formula is C2H4O2. And again, its empirical formula, we can divide by 2 for the carbon, hydrogen, and oxygen atoms, and we get CH2O. And again, we have the structural formula and the ball and stick models showing how these atoms are connected. Isomers are compounds with the same chemical formula, but they have a different structure. So the difference in structure gives them different chemical properties, despite them having the exact same numbers of each of the individual elements. So an example is acetic acid and methylformate. They both have C2H4O2, but they have very different properties. So here's acetic acid, and here's methylformate. These are structural isomers. And so they have the same number and type of atoms, but they're arranged differently. And so this makes these two compounds have different behaviors and different functions. This is another example of a spatial isomer. Excuse me, this is a spatial isomer, but it's still considered an isomer. The last one was a structural isomer. This was a spatial isomer. Um, Carvone is it is this seed. We write it as plus carvone, and the other type of carvone is in a leaf form, and we write it as negative. So that's another type of isomer. All right, and here are the questions associated with this section.